Cool, well, goedemorgen and welkom op GDevCon nummer 3. My name's Larry and this here is Leah and we are from Dyson and we're proud sponsors of this fantastic event, GDevCon. Really enjoy it. So, what I wanted to have a little chat about to introduce ourselves is who is Dyson for anyone who doesn't know. I mean, it's a popular name, but there's interesting facts I can sort of provide you about how we got to where we are now. And then what I'll do is I'll hand over to Leah to talk about what we're here actually to talk about, which is G, which will be quite fun. So G at Dyson. Cool. Right, so where did it all start? James Dyson, by himself, he was lucky enough to be able to spend time trying to persevere inventing this new invention that he called the dual cyclone technology. The idea behind it is that it's a separation system to separate particles from the air without the need for a bag, but also, in so doing, increasing the performance of airflow through the unit itself. So, after about 5,127 prototypes, he landed on the Dyson DC-01. And the Dyson DC-01 was the first bagless vacuum. You can see it here on the left. Now, to get it to production state, back in 1993, the engineers working on it were all mechanical engineers. There were 5 of them, and it became a complete success. Looking to today, on this side, we've got a V15. As you can see, we've got so many more components and so many more sensors and various other things that we need to be able to cover that we have over 400 engineers working on that one product, and that's just R&D. So, we have a whole bunch of categories that we are currently working on, and we're always looking to innovate further. We've got our floor care and our environmental care products, like our fans. We've also got hair care products as well, which are incredibly popular, and who knows what new technology we will be coming out with soon. So, where are we based? In order to cover all of these different technologies, we're based around the world. We've got campuses in the UK, over in Singapore, Malaysia, China, and in all of these sites we do various R&D and advanced manufacturing as well of our products. So, to give you a few pictures, on the left there we see we've got Lavington and Malmesbury. Those are based in the UK. We've got a Shanghai Tech Centre, the Philippines Advanced Manufacturing Centre where we generate our motors. We've also got a brand new Singapore St. James Power Station, which is an iconic building in Singapore, which has been renovated with very tactfully, and they've kept as many of the original features as possible, what made it into this amazing office to work at. Since 1993, in the UK alone, as an example, we've invested, I say we have invested, James Dyson has invested over £1 billion just on generating the campus that we are in. And if we actually looked across the world, we've got over 800 acres of space to do R&D, which is quite a lot of space, ready to expand further. Now, of course, with all of this expansion that we've had, one key problem that we always find is finding talent, finding people to actually work for Dyson and provide us with the skills we are lacking. So back in 2017, James Dyson decided to set up what was called the Dyson Institute of Engineering Technology, which is DIET. And that was a university partnership with Warwick University where we accepted up to 40 applicants in the first year. Was very highly subscribed to. It's essentially a university degree paired with actual on-site real work on real projects. So it's a full 4-year course, and in 2021 we had our first full graduates, so they got their degree, and of those graduates, 33 graduates, every one of them's decided, not obligated, but decided to stay full-time at Dyson, which kind of shows the cool projects that we have available to work on. So, looking to the future, we're always trying to solve problems. We want to be the first. A good example here is the Dyson purifying headphones, the Dyson Zone. You may have seen this on YouTube. It's essentially a new type of project and product for us. It's essentially taking our products but outside the home. It's quite an exciting thing, and there's plenty more to come along as well. So, to hand you over to Leah and talk about something that we're really interested in. How are we going to meet all of these lofty goals when talking about G at Dyson?
Thank you, Larry. So here at Dyson, we have an awful lot of LabVIEW and NI experience in-house, with a number of these users, 132 users last time we counted, and a number of these being certified. The sort of teams that our users work in, it could be things like research and development, it could be motors and power systems, it could be manufacturing, it could be things like electronic system test as well. With all of these users, the way they share their knowledge is through our quarterly internal user group. We have forums such as our Teams channel, you can see up here, and we also do code reviews within the team. With so many users, it's important that we can share our code. Like a lot of you out here, we use Git as our source code control, and alongside this, we use the Atlassian toolchain. So that's things like Jira for issue tracking, Bitbucket, and Confluence. We have a lot of LabVIEW users, but alongside this, we also have a lot of test stand users and VeriStand users too. And a lot of the test teams will use tools like TestRail for their test management. We tend to do a lot of collaborative work, and I've just included this graph here. It's something I took from our test stand common repo, our Git repo, which has our abstracted device drivers for some of our test stand tests. And you can just see, I've blurred out the names, but just how many different people will contribute to these sort of projects. And it's really great just to be able to learn from this many people. It's also important that we can deploy and share our code. So again, like a lot of you, we use NI packages quite a lot. Sometimes some teams will deploy these via system link to different targets, and we also use VI packages for packaging up tools. Something that we often end up packaging up is bespoke hardware drivers, because we find that a lot of the measurements we need to take, there just isn't the hardware out there, so we make our own. An example of this would be those bottom two pictures. That is the intelligent orifice control that we use quite a lot. That is a restriction control for airflow. Some other examples of rigs, above that we've got a airflow characterization rig, and that one in the middle there is a push-pull rig for continuous testing of vacuums. So I'm going to take you through a case study on one particular system, which is the Apollo rig. The Apollo rig is a test and measurement system that uses standardized hardware to take the wide range of measurements that we need to be able to take on Dyson products. So we tried to make something really redeployable and reusable, and that we can use on a variety of different products and projects. The way that we accomplish this is we have our instrumentation at the back there, and it's split away from our device under test with a custom designed mass interconnect. So we just connect up whatever sort of measurements we need to be able to take. At the moment, we have 30 of these systems deployed not only in the UK, but in Malaysia and Singapore. And we're also looking to make more of these soon. They run unmanned, so it's important that we have safety systems in place. And it's also important that we can deploy to them in a scalable way. So we use the tools that I mentioned earlier for this. As Larry mentioned, there's a lot of opportunities at Dyson, both currently and upcoming. So I've brought along a video today from Jake Dyson outlining some of these opportunities in the robotics area. And you can find these on our website if you search LabVIEW. Thanks a lot.
Thank you.
It is very exciting. I'm not sure there are that many people doing this sort of stuff we're doing out there in the world. So this hangar over here, this hangar 86, is completely full of engineers working on wearables. In this building, we're focused on robotics. So this building is full of robotic engineers, but we're working on very, very exciting robotics projects. So for the last 10 years, for example, we've been sponsoring the Imperial College. So actually the work that's going on in these PhDs is ripe right now. So we're setting up a robotics tech office in London, as well as Singapore and here. So between the 4 locations, in effect, bringing everything a bit closer into the live projects we're working on. We've been working for about 20 years now on floor care robots, which are puck format robots. And ours really do vacuum, by the way. But aside to that, we've also been doing a lot of research into robotics over the last 5 or 6 years, which no one's aware of. The subject, what you're actually developing, accounts an awful lot in terms of excitement and attracting engineers. The tricky thing is that we can't overtly go out there in the world and say, hey, this is what we're doing, because it's very top secret. This is why we want to reveal a little bit more to the world. We're after 700 engineers in robotics. That's what we're looking for, to work on the brain, robot brain, essentially. We're a small team of experts doing big things. And we can get there, but we need more people. Yeah, this is Hangar 85. And the engineers are laid out to support the way a robot system works. Now, it's a bit hard for me to climb over.
Yeah.
So
it's basically deploying advanced robots in household environments for mapping the environments, understanding the structure of the household.
There's a big future in robotics. It's saving people time, performing chores for people, and improving people's daily lives. I mean, I'm a parent. I've spent half my life cleaning up after my kids, and it's pretty tedious. I was a bit shaky when I come in here, but we call this an arm room. This arm here, we've had to write software for to measure and calibrate its movement through its entire articulation. And the computer here senses any interruption or force.
And it needs to be as compliant as possible and safe in a home environment. Is it able to take impacts like this? Once we add a soul to it in software, we are able to understand its limitations and give feedback to the mechatronics team to improve them.
And at the end of an arm, you need a hand. And a hand needs to be designed to grip, manipulate, pick things up.
We're trying to achieve something that's very, very complex, that no one has achieved so far.
And so there's more testing here where this arm is actually looking at the object and analysing what that object is, to how the best way to pick an object up is. Over here, there's a very, very exciting rig. So what this arm is doing is it's able to map that chair in 3 dimensions. So this means I'll never, ever find crisps down the back of my sofa again.
Hopefully not.
Ever. So you're coming in here. So this lab is the perception lab, okay, and this is all about the brain, about the vision systems, how the robot is interpreting the environment through sensors, cameras, thermal imaging, being able to map humans and navigate through the world.
The head has a pan tilt mechanism, so it can move this hammer up and down and move around. It has these back-to-back fisheye cameras, which is one of the most important things we see is needed for the robot.
The focus here is to use robot learning or reinforcement learning to teach robots how to handle these objects. And it's actually inspired from child psychology. So when a robot successfully picks up an object, we give it positive reinforcement, and when it fails, we give it negative reinforcement.
So this is actually all of the elements that we're working on separated out in research. And this is kind of like the first stab of bolting all of those elements together and it working complete as a system.
So we are literally building an artificial being from scratch and then having to populate its brain with AI and vision and general perception and controls.
It's highly complex stuff, and every single element in engineering needs to be solved and thought about, right through from the sensors, the electronics, to the actuation, and then the environment that it's working in. But there's also things we're learning that we can feed back into the other products and the other categories to enhance their functionality and performance for consumers. One of the very exciting things about robots, as with wearables, is they are the future of Dyson. We're looking forward to a 10-year lens and further. We've always done that We've always invested in the future with the digital motors, with batteries, and knowing what we want to invest in and drive towards.